Hi, I'd like to review a few of the concepts we covered in the class on Monday and just review a few little things and give some more details. So here's a presentation. So here's a concept related to mirrors. So if we have an object like a happy face on one side, we end up with some light being reflected off of the object. And if it's at a distance, we view these lines as being parallel lines of light rays, and they actually will hit the mirror surface and of course be reflected off the mirror. And we get to think of some of the laws related with this. So if we look at this top line as a light ray, which is called an incident light ray being brought in from the object, we have an angle to be aware of. So you can draw a line perpendicular to the mirror, which is called normal to the surface, a normal line. And then if you measure the angle between this blue line and the normal line, you will get what's called an angle of incidence. So that circle that has a line through it, that is called theta. It is a Greek letter that stands for an unknown angle, basically. So you will see this a lot in high school. Theta, so just a circle with a line in it, and then beside it is I, indicating that is the angle of incidence. So the angle that is tied to the normal line coming out of the mirror. Okay, and then all these lines will be reflected, and whatever angle is here, the angle of incidence, will equal the angle of reflection. So you will actually have, if there is an eye to an observer here, that person would see this happy face. But if the person were farther up and their eye is there, you would see, if you draw the line down and then up, that person would see something else in the mirror, in that location on the mirror. So it just gives you a little sense of how these things are bounced around. The angle of incidence is equal to the angle of reflection. That is called the law of reflection. So when you have paper, it does do reflection. I forgot that there's a typo here, does not. The angle of reflection doesn't work the same as with a mirror. And it's because the surface of paper, even though it looks so flat, if you look under a microscope, it's quite rough. And so those reflections bounce off in all different directions. So the angle of incidence no longer equals the angle of reflection. So as a result, instead of being able to see a nice clear happy face in the mirror, or on the paper in this case, you will only see reflected light off the paper because it all gets diffuse reflection, so you don't get a nice clear image in any which way. So again, this is reiterating the idea of, if you have the happy face up here in the corner and you have an observer over here, an eyeball over here, the angle of incidence of seeing something up here will then equal the angle of reflection for a mirror. Okay, so this shows you that if you have a converging lens, which is what our eyeball basically is, there's a lens on the front that's converging, it will pull all the information, light rays from the top, for instance a tree, through the lens, and it'll end up on the bottom. And then the bottom part of the tree will go through the lens and end up at the top. So the interesting part about a tree, or any object really, is that you end up seeing the image upside down on the back of your eye, called the retina. Now, the interesting part is that your brain plus the optic nerve will send the information, rectify it so that we see everything properly right side up for ourselves. And this optic nerve that is in part of the back of your eye, That's a blind spot. It's not a part that is receiving information of what the image should look like, but our brain fills in that bit of information. So this here, you end up with, if you have an object placed in front of a concave mirror, you can do some calculations and you can do some drawings that makes one aware of what's going on that way. So what do we have? We have an object here, an arrow that is placed some distance from the mirror, and you have a focal point. Now, what is the focal point? It is half the radius of curvature. Okay, so whatever, if you were to continue the circle for the mirror, you would have a center. So the center is right here, I'm sorry. And then half of that would be your focal length. Okay, so that's where it focuses. And you have an object. So from a drawing perspective, what you can do is you draw a line straight out, parallel to the line that's the middle line. And then this is a little trickier and I had to kind of eyeball it, but you want a perpendicular line coming out of the page that would be perpendicular to the curve. So like roughly where the curve is straight, which is called a tangent, if you've learned about that yet. And then you draw the line through the focal point. Okay, so you draw those two lines through and you continue it across. Now we have another one. You draw from the image straight through the focal point, and then you're going to draw that parallel to that middle line. And those two lines will converge here. Now you can also draw a line from the center, the radius center. And all those, I mean, as long as you have two of them converging, you will know where that image is showing up. And that image, as you can see in this case, is larger and upside down or inverted to the object. So if a person were looking at this from this location where they can see all that light, they would see an image that is upside down and larger. And when you look at things that you have a concave mirror, you will see that's what happens with them. Now, with a convex mirror, so remember you've got concave is on the inside and convex is on the outside. A convex mirror is a little bit different. I found these drawings would be very taxing to do in PowerPoint, so I ended up hand drawing them. But what you end up with, you have an object and you draw a straight line across and a line through the focal point. And then you do the other one. In this case, you get thinking about the only easier way of doing it is you draw a line from the object straight through the center of radius. So this radius again would be this 90-degree aspect to a tangent line of the circle, if you know about that. And you can see where those two lines converge. And that's where the image will show up. Okay, so the image on our concave mirror ended up on the same side as the object and the observer. But on a convex mirror, it ended up right side up and it ended up smaller and behind the mirror as such. Now you're only going to see these images on the mirror surface as such, but if you do the calculations and see where these rays, it's like it's being projected to inside or outside the mirror, which is kind of a funny concept, I know. So what you end up with these convex mirrors is you're bringing more picture into the mirror and condensing. So everything's a little smaller, but you're seeing more picture. It's bringing more field of view in. Okay, so positive or negative for mirrors. Well, we get to think about this a little bit. I kind of missed my drawing feature on this, but anyway. So if you have any type of mirror is the line, but you can have it curved, of course. You have an observer on one side. The biggest thing that I stressed on this is the math calculations are not that hard, but you do get to try to figure out which things are positive and which things are negative. So anything in front of the mirror ends up being positive, which I'm not sure I said that properly in class on Monday. I'm not certain. So anyway, our focal point that we use should be in front. The object, of course, will be in front. It would be really hard to put an object behind a mirror and still make an image show up on the mirror, right? So an object will always be in front. And then if the image ends up in front, all these things end up being positive. Okay? If any of these things end up in the back and behind the mirror, then they are negative. Of course, you'll never have the object be behind the mirror, but you can have the focal point being behind there and the image being behind there. And then you get to put negative signs in front of those distances of images and focal points and that sort of thing. Okay, so here are the formulas that you end up using for this. They're not that hard to use. I mean, these are the only ones that I've really used in grade 11 or 12 for a week or two. And what it was is you have magnification, did it get larger or smaller, is equal to the height of the image divided by the height of the object, which is equal to the negative distance of the object divided by a distance of the image divided by a distance of the object. So you are usually given 3 out of the 4 of these things or 4 out of the 5 and you get to solve these. Okay, so the manipulation there is not that hard. And then you also, sometimes you need one piece of this, so you use the other equation or vice versa to get all the pieces. And the other one you have is 1 over the distance of the object is plus 1 over distance of image, which is equal to 1 over the focal point. I like to put it the other way, 1 over focal point equals 1 over the other things. But anyway, it's the same difference. And then the last thing you have is the focal point is equal to the radius of curvature divided by 2. That's nice and simple. So these are the only equations you use at like a high school level. This is where we start getting into how to calculate things. There's a lot on this page, I will admit this, but I give you at least a little bit of a visual. You have some object that is 1.5 centimeters high, this green arrow thing. So that's the object, and it's placed 20 centimeters away from a concave mirror. And then you have a radius of curvature for the mirror of 30 centimeters, which means if you divide it in half, you get the focal length of 15 centimeters. This is definitely not drawn to scale, as you can see right away. So you can determine all kinds of things just knowing this amount. You can also do the drawing. You can draw across and then through the focal length, and then you can draw through the focal length and across, and then you're going to get this projected image down below that we worked on in the other slide. Okay, so you can play with doing that as well. So what do we have? We have the focal length being half of the radius of curvature. Then we use this lovely formula right here. You have the distance of the object and you have the focal length. So you can solve for the distance of the image. The biggest trick is to be aware of which things are positive and which things are negative. And everything ends up being on this side, which is the side that ends up being positive. So we're going to end up with a positive distance of the image, which would be, you'd know that right away from your calculations if it ended up being positive or negative. Okay, now you have almost everything. You don't have the magnification quite yet, and you don't have the height of the image. But you do have height of object, you have distance of image, you have distance of object. So if you rearrange, you can get the height of the image, and it is negative 4.5 centimeters. What does that mean? It means it's going to be 3 times larger, and it's going to be negative in this. When it's height, negative means it's inverted, so it's going to be a negative height. upside down. And remember, those concave mirrors are upside down. And your magnification is going to be -3, 4.5 divided by 1.5. The negative means it'll be upside down, and the 3 means it's 3 times as long as the original object. So that gives you a little sense of how to do the math on these. Okay, so this gives you a comparison of lenses. And these lenses, when we get thinking about them, if you have parallel lines, it's representing something very far away that's sending the light across. Okay, so you kind of approach infinity type thinking, seeing far away. You could have the person's eye over here, some sort of image like a tree quite a ways away. And what happens is the light gets bent through the lens. Remember Snell's law, as things travel through different media, the light can be bent at different angles. So you get this angling effect and you get a focal point. Okay, so everything gets focused in on something. When you think about a magnifying lens, heaven forbid, don't do it, but you can put a magnifying lens, let the sunlight hit it, and then you're going to see all that light narrow into a point you could, in theory, start a fire. Okay, so it's this converging of all the rays. Then you have the opposite where you have diverging lens, where all those rays get even bent farther away from each other. So the person's eye could be over here and the focus is being brought in the opposite direction. So the focus is on the other side, whereas for a converging lens, the focal point is on the same side as the eye. Okay, so it just gives you a little sense. So here's a picture, it's reversed, but you have something that's far away and it's being bent in, so the focus is being tunneled into a certain area on a focal point. Whereas if the lens is the opposite, what are we getting? The rays of light are being bent out from each other, and then you get a focal point on the opposite side from the eye, which is kind of interesting to think about. Okay, so here's a diverging lens, and this is the sort of drawing of rays that we did with the mirrors. If you're like, whoa, there's an awful lot of lines, this gives you a little sense of it. Again, we're at grade 11, grade 12 here. So here is an object, and what you do, you draw a line straight out, okay? And then you would be able to draw a line from the focal point to there, and then you continue it out. And where are the lines going? They're being bent this way. Now you've got it going all the way to this line, which is handy. Now you can also draw, like we did before, you can draw a line straight through the focal point. We're not getting any convergence of lines at this point to know where the image is. So then we have one additional where you can draw the line right through the middle. Okay, and when you draw the line right through the middle, you're taking a line that is essentially, it doesn't show well on this picture by any means, but it's doing a perpendicular to the curving at this point. Okay, so you have a convergence of the two lines right here, which shows you where the virtual image is going to be. Okay, so it gives you a little sense of the object was way larger, the image is smaller, and the person is going to see the image as smaller if this is the lens right here. So they actually even have to calculate the distance of the eye to the lens and what that's going to do to the images and how it's going to project onto the back of the eye, all that sort of stuff. It's very complicated. Okay, here's a further rendering of the same thing, and you can see that we use the equations. You can also use the lines. If you measured everything to scale, it would work just fine. So you have an object, you draw right through the center of the lens, and you also draw one that goes straight across, and it's got to go through the focal length. Okay, and the actual light is going to travel this way. Now where they meet, that's where your virtual image is. And then you have the distance of the object, object to lens, distance of image, image to lens, and then focal point is being used on this side. Okay, so then you have to be aware of what will be positive and negative for your calculations. Okay, so here is when is it positive or negative? And guess what? That I find a bit of a challenge myself. I will admit that. So what are you dealing with here first? Well, the object is on the opposite side of the eyeball. That's kind of where it should be, is the way my brain thinks about it. It's not going to be working on the same side. So that one's always positive and always going to be over there. What else do we have? We have a focal point. The focal point that's being used for the crossing through to find the image is on the side as the same side as the object. I like to think of that being needing to be on the same side as the eyeball. So the way my head goes with this is you should have the image on the side as the eyeball to be able to be projected on the back. Doesn't quite work that way, but that's the way my head works well with it. And then we also have the image is negative because again, you really should be having the image close to the back of the eye sort of thing is the way my head gets it straight, even though it's not quite right. But anyway, what you want is focal point should be between the eye and the lens, image should be between the eye and the lens, and object should be on the opposite side. And that's what gives you everything being plunked into this lovely formula as being positive. If your image and focal point ends up being on the other side, so they're ending up over here this time, they should be sitting over here. So they're going to end up being negative designations. So if you have distance of image, it's going to be a -2 or whatever number it is. And just gives you a little sense of that. I find the sign part the hardest on. Okay, so for this, all I'm trying to show is that depending on what book or what you're reading online, that it will sometimes use different designations. So I was using 1 over DO plus 1 over DI equals 1 over F. Well, in this case, they're just using 1 over O, 1 over object plus 1 over image sort of thing. So you can have different ways of the writing of the equations, but they mean the same thing. I'm covering this one portion here, but magnification equals -I over O. That would be distance of image over distance of object. And then it's h prime, that little one on top, divided by h, or on top of h. So that is height of image. So they're designating the little prime as being image, and just an h, which you can't see through my picture here, as being the height of the object. So same designations, just using different letters to do this. So when you have a convex or converging lens, this is when stuff is positive. When you have a diverging lens, your image and your focal point and all ends up on the same side as your object. So with a converging lens, you're dealing with the focal point over here, you're dealing with the image over here, and this is just kind of what I think has to be sitting on the same side as the eyeball to interpret. It's not correct, but that's how I keep it clear in my head. So in the case of your convex lens, everything is positive. In your case of the diverging lens, your focal point and your image end up often, almost always, I think, negative because they'll end up over here. Okay, with this slide, I have not really, I did a little bit a long time ago of calculating two lenses being combined and where does the image work out. You solve one lens and then plunk in that information in as being sort of the object for the next lens. That's what I do remember from it. And what you can see and appreciate is that the math gets a little more complex. How the images end up looking gets more complex because one gets fed into the other. And when you have lenses for in glasses, you get combinations of multi-lenses to make the right amount. So one side can be sort of diverging and the other side can be convex. That definitely shows up in my glasses that way. And you get this combination to be able to correctly portray the image in the right way. Because even remember, some of these images end up upside down. And if you had the image upside down even before it got to your eye, that could get complex too. So you can appreciate that an optometrist has to study an awful lot. And here is our last slide. This one I just thought was kind of interesting. There's this thing called the poisson. Poisson is French for fish, by what I remember. And this is a guy's last name, Aragon spot or Fresnel spot. So these are all different scientists at the same sort of era. Fresnel realized that light traveled in waves. And this Poisson guy, this was during a sort of science competition at the time to come up with ideas and see who wins sort of thing. Poisson believed it was still light waves were particles traveling. So some of the math works that light travels as waves, and some of the math works as light being particles. So we're trying to fit light to match into boxes that work for us, right? Nature does what it wants to do. So what has happened is there's this, Poisson knew that if light traveled in waves, then if you had a shadow, you would have a bright spot in the middle of the shadow. And when I was reading this, I was like, wait a minute, I've never seen this. And I never really thought about this. So this was new for me to ponder. But I thought it was kind of cool. So anyway, if you have a light source and you have a nice circular object, because then you're going to get all kinds of bending and sort of converging on the same spot, then it works. So you need something circular. And you need a really nice strong light. Laser works really well. And what happens is the light will bend around the sides of the object a little bit. And that light travels in waves. And one of the ways, I can't draw this because it doesn't work in this format, but instead of just a line, you would have a curve this way. And you'd have more and more curves spanning out. So each one of these lines would be a whole curve. And then on the other side, you have the same thing. So you've got the light wrapping around the object and you get these wavelengths going this way. Okay, and these curves where the lines are. Just give you some sort of visual idea on this. And in the middle, those wavelengths are crossing paths. And they cross paths in a nice, perfect way to give you a light spot in the middle. And Poisson is like, see, this doesn't work because none of the shadows have a light spot. So Fresnel was kind of discouraged. But then there was this Aragon guy who did some further experimenting, and he was able to, he used stronger light and more perfect circle or whatever, and he ended up proving there was a bright spot, which indicates that light does travel in waves, and the waves are represented by these curved circle lines, okay? And what we know from this, Poisson, it's kind of funny to find this out, Poisson was given the name of this spot, so was Aragon and so was Fresnel. I guess all three got some recognition on this, but Poisson never believed this was actually the case, that light traveled in waves. So he got accredited for something he didn't believe in, which is kind of a funny way of dealing with things. So anyway, I hope this is kind of interesting. You can see lovely videos on how this is set up and see the spots in the middle of a shadow. They're only like 5-10 minute videos. So that just gives you a little sense about the bright spot in a shadow. So I hope this covers the material a bit better than the first time. We'll see you next week. Bye.